Look closely at a heavy-duty marine rope. The physical strength required to hold thousands of pounds of tension against the ocean is significant. We see that same durability in high-stress automotive gears and high-tenacity industrial carpets. Despite looking and feeling entirely different, these materials are chemically identical. They are all made of nylon 6. This pie chart breaks down the global market demand for that specific material. Textile filaments represent 41% of the market, while resins and films account for another 26%. To meet this worldwide demand, the industry manufactures over 5 million metric tons of nylon 6 every year. But before a single thread of nylon can be spun, the production pipeline relies on a single chemical precursor, a molecule called caprolactam. In its raw form, caprolactam is a white, water-soluble solid. Chemically, it's classified as a cyclic amide, a molecule where the atoms are bonded into a closed loop. The industrial synthesis of this specific molecular ring is what provides the building blocks for the nylon 6 used in these heavy-duty applications. Building that ring starts with basic hydrocarbon liquids, usually cyclohexane or phenol. This flowchart outlines the pipeline converting raw liquids. First, cyclohexane or phenol is oxidized into cyclohexanone. Next, treatment with hydroxylamine transforms it into an intermediate, cyclohexanone oxime. This leads to the critical phase, introducing strong acid to trigger the Beckmann rearrangement. At the molecular level, the acid facilitates a structural shift. It forces the existing 6-carbon ring to break open and incorporate a single nitrogen atom into the gap. The molecule then settles into a larger 7-membered ring. This reaction is difficult to balance. Expanding the ring generates significant amounts of ammonium sulfate, a byproduct that chemical engineers work to minimize in industrial practices. The Beckmann rearrangement is an energy-intensive industrial hurdle, but it's the necessary path to creating the specific molecular geometry, giving nylon 6 its industrial utility. So why expend so much energy to build this 7-membered ring if the goal is a long-chain polymer? The structure is built specifically so it can be controlled. To make nylon, manufacturers use a process called ring opening polymerization, where they snap those rings open to link them together. In manufacturing, this process is triggered by heat. The caprolactam is melted down inside industrial molds. Under that heat, a chain reaction takes place. Individual caprolactam rings break apart and bond end to end to form massive repeating chains. This polymerization is what transforms the monomer into the durable solid we recognize as nylon 6. Because the process is so essential to the plastics industry, companies like BASF, Toray, and DSM develop proprietary methods to maximize the efficiency and yield of this reaction. Mastering the expansion and opening of the caprolactam ring provided the scalable chemical foundation for the nylon 6 products that have become standard in textiles and engineering resins. But scaling that chemistry to 5 million tons a year requires a massive industrial footprint. High-capacity facilities like this must run continuously to meet global demand. There is also a direct atmospheric impact. Synthesizing these carbon rings produces nitrous oxide as a chemical byproduct. Nitrous oxide is a potent greenhouse gas. In the atmosphere, it traps significantly more heat per ton than carbon dioxide. Yet, unlike many other industrial emissions, nitrous oxide from caprolactam production is currently unregulated in most countries. This has led to a push for new production methods. Researchers are developing bio-based pathways that could eventually synthesize caprolactam without relying on petroleum precursors. There is also a focus on recycling. New chemical engineering methods aim to depolymerize waste nylon 6, extracting pure caprolactam from discarded plastics to be used again. The caprolactam ring remains a vital component of modern material science. However, maintaining its utility in a more climate-conscious world requires us to engineer a more sustainable way to build and recycle it.